So in the 2015 AFC football championship game between the New England Patriots and the Indianapolis Colts, there were 11 of 12 footballs provided by the Patriots that were inflated to a pressure of 10.5 psig, so pounds per square inch gauge, as opposed to the NFL required pressure range of 12.5 to 13.5 psig. So this was known as Inflategate or Deflategate, I guess was the name of it, or Balgazi at the time. And so there were accusations of cheating since the Patriots quarterback Tom Brady had made statements earlier that he preferred underinflated footballs since they're easier to grip. And I guess that's pretty common among quarterbacks. So there was some debate about this. There were some studies found. They never really did conclude that any cheating occurred, but it was all very suspicious. And so created this little problem related to that event. And so the situation that we're going to deal with here is we're going to assume that we're at the minimum NFL required pressure of 12.5 psig while in the indoor room, which is held at 68 degrees Fahrenheit. So the idea is that the footballs are inflated in an interior room that's held at 68 degrees Fahrenheit to the lowest pressure that's allowable by the NFL. And then we take those same footballs and bring them outdoors where the temperature is a little bit lower. So the game day temperature, I think, was 51 degrees Fahrenheit. And I'm curious to know what is the ball air pressure when you go from 68 degrees Fahrenheit to 51 degrees Fahrenheit? Would that be enough to drop the pressure down to the 10.5 psig? And then we're told that we're going to assume that the atmospheric pressure at the start of the game was 14.64 psia. That's the pressure that you'd have at the particular location for the 51 degrees Fahrenheit. So the way we're going to approach this problem is we're going to use the ideal gas law. And if you just remember, the ideal gas law is the pressure times the volume is equal to the mass of air in the ball times the gas constant for air times the absolute temperature. So there's the ideal gas law. And since we're dealing with a football that's inflated, we move it from the inside to the outside, it's the same mass of air. Okay, and the other thing is that we're going to assume that the volume of the football is nominally the same as well. So even though the football has some elasticity to it, it doesn't change its volume to any significant degree. It's not like a balloon. The material is relatively stiff. So once it's pressurized, the volume doesn't change very much at all. It's only when it's very low pressure do you start to see appreciable changes in volume. So we're going to assume that the volume remains nominally constant as well. So the volume, the mass, and the gas constant all remain constant. So then what we'll end up with is P1 over T1 is equal to P2 over T2, where the 1 here indicates the pressure and temperature inside the room, so the 12.5 psig at 68 degrees Fahrenheit. And then P2, T2 are the conditions outside. So there the temperature is 51 degrees Fahrenheit. And we're going to try to solve for the pressure. So let's rearrange that. So we're trying to find P2 given the temperatures both inside and outside, and then the pressure on the inside. So in order to do this calculation, we need to make sure we're using absolute pressures and absolute temperatures because we're using the ideal gas law. So this pressure needs to be an absolute pressure, that needs to be an absolute temperature. So to get the absolute pressure, just keep in mind that we are given the pressure in terms of gauge pressure, psig. So we want to convert that to an absolute pressure. So that would be 12.5 plus the surrounding atmospheric pressure, which is the 14.64. And that makes it pounds per square inch absolute. Okay, so when you plug those numbers in, that comes out to be 27.14 pounds per square inch absolute. And the absolute temperatures, so we start at 68 degrees Fahrenheit. And to make that an absolute temperature, to turn it into degrees Kelvin, you add in 459.67 or 460 degrees, and that'll make it into Rankine, degrees Rankine. So if you plug those numbers in, that comes out to be 527.67 degrees Rankine. And then temperature 2 is the 51 degrees Fahrenheit. So that'll be 51 plus 459.67 to make it an absolute temperature. So that comes out to be 510.67 degrees Rankine. So now we can go ahead and plug these back into this expression right here and calculate what the pressure is outside at the 51 degrees Fahrenheit. When you plug those numbers in, it comes out to be 26.3 pounds per square inch absolute, and so we'll make that a gauge pressure. So what we're going to do here is subtract out the 14.64, and so that becomes 11.6 pounds per square inch gauge. So that's the pressure we would expect just from the temperature change. So this was one of the explanations people used for why the balls were deflated, was that it was warmer in the room where it was pressurized to the minimum, and then when they took it outside, it was colder, and so the pressure would go down. And indeed it does. It goes from our 12.5 psig down to 11.6, but that's still not down to the 10.5 that was reported being measured. So it wasn't just the temperature difference that was enough to cause the ball to be at too low of a pressure. And in fact, in order to get down to the 10.5 psig pressure, when it was filled up to if you fill it up to 12.5 psig in the room, that temperature, so you could work it out to figure out, starting at 12.5 psig to get to 10.5 psig, what starting temperature would you have to have? And that temperature would be something like 91 degrees Fahrenheit. So that's very unlikely. You're not going to have the indoor rooms up over 90 degrees, right? So that's not likely to occur. Another possibility is maybe there was some moisture on the ball, and so when you bring it outside, that evaporates and drops the temperature on the ball surface a little bit more to make it colder than 51 degrees Fahrenheit. That again is very unlikely. So that's not a good explanation. So in the end, there really wasn't a good explanation for why the pressure was as low as 10.5 psig. Just a simple ideal gas calculation shows it wouldn't have dropped that much. So I won't make a conclusion here. You can draw your own conclusions about what happened. There may be some other effects that occurred that we're not considering in our model, for example. But certainly, just from the ideal gas law, just the change in temperature from an indoor room to the outside is not sufficient to get to that pressure that they reported when they took the ball, when they measured it outside. We would only get to 11.6, not the 10.5. So something else was going on. That's all we can really conclude at this point. All right, anyway, I thought that was an interesting example. You can read more about this event online if you go to this Wikipedia page.